determine if these materials are linked to illegal drug manufacturing. Let's start by assigning tasks and techniques. Jacqueline, can you show us through your sample prep in detail?
I already log out all the evidence and maintain a proper chain of custody. So for the white powder, I use a clear spatula and transfer it into the small and liquid into the GCMS swab. So for the white residue is flaky and might be volatile, I use a sterile scraper to scrub it down and transfer them to the sterile petri dish. And for the third is a torn fabric. So this fabric might consist of trace residues. So I use the tweezer to mount them on an SEM stud with conductive tape and to avoid the static interface. And lastly is the correct letter. They are rid of chemicals. So I swab them with the corrosion side with distilled water and collect the residues with the bag swab separately to preserve the acidity.
For white powder, I recommend using GCMS to identify any organic compounds like drugs or any cutting agents. And for the wall residue, I believe that FTIR can detect chemical functional groups and the fibers should go under SEM to check for any particulate contamination. And the metal tools would need X-ray fluorescence and energy dispersive X-ray spectroscopy with SEM to test for any corrosive chemicals like acids or of course solvents.
Solid plans, guys. So Jacqueline, any risk or contingencies?
The bigger risk is degradation. The powder might be oxidized if exposed in air too long. So I work under the fume hood. For the more residues, could be hydroscopic, meaning they will absorb moisture. So I will store them with the desiccant packs. For the metal tools, their corrosion might be reactive, so I will wear a double glove and safety goggles when swabbing it.
Alright team, let's head to the lab. Alright everyone, let's begin with bag number 1, the white powder. The key forensic question is this powder an illicit drug or another controlled substance?
Here's the alleged white powder, Lamia. Please handle it with care.
Of course. So, GCMS is ideal because it's highly sensitive and accurate in identifying organic compounds. It can separate the components of a mixture and match their mass spectra to known substances in a drug database. So first, I dissolve a small amount of powder in a solvent, filter it and inject it into the GCMS, and the gas chromatography separates the compounds and the mass spectrometer provides a fingerprint of each one. The powder contains cocaine hydrochloride, confirming the presence of an illegal drug.
Damning evidence. Jacqueline, what about the wall residue?
Prep and ready for FTIR.
Now, let's see if this residue is an explosive material or a combustion byproduct.
FTIR identifies the chemical bonds in organic and inorganic compounds. It's non-destructive and can quickly detect residues like nitrates or hydrocarbons, which is common in explosives. I will press a small sample of the residue onto the ATR crystal and start the scan. The resulting IR spectrum shows peaks consistent with ammonium nitrate, suggesting the residue could be from an explosive substance.
Explosive substance. That is shocking. Damia, simulate the SEM for the fibers. Can we determine the type and possibly the origin of this fiber?
SEM provides detailed surface morphology and can determine the structure of the fiber and also the elemental composition. So SEM reveals the fiber's morphology matches polyester, suggesting imitation fiber which should be potentially useful in suspect profiling.
Let us move on to the corroded metal tool. Now, what type of metal is this tool made from and what caused the corrosion?
SRF is a non-destructive method that can determine the elemental composition of metals. EDX paired with SEM gives a more detailed view of surface corrosion and elemental mapping. I find the tool is primarily made of iron with traces of chromium, likely stainless steel. SEM EDX analysis reveals splitting corrosion and chloride presence, possibly due to exposure to salt water or any acidic chemicals.
Nice catch, Damia. Alright team, organize your findings thoroughly before we head to the evaluation panel. Ensure all documents are secured with clear reports. Alright, good afternoon everyone. We are here to present our forensic analysis of samples collected from a suspected drug manufacturing site. Our team employed substance, explosive residues, and chemical corrosions linked to illegal activity. Jacqueline and Damia will walk you through the evidence.
As I have compiled in this report, bag A contained white powder analyzed via gas chromatography mass spectrometry. This technique separates mixtures and identifies compounds by their mass spectra. Results confirmed that the powder was cocaine hydrochloride, a Schedule II controlled substance. The presence of levamisole, a common cutting agent, was also detected.
So the chain of custody was remained, and there is no sign of tampering.
So, could the cutting agent suggest a specific supplier?
So potentially we flagged the levamisole for cross-referencing with DEA databases. However, limitations include sample degradation rates due to improper storage at the scene, and co-elution of cutting agents make quantification difficult. We need LCMS for better separation.
The war residue were analyzed using FTIR. So the spectrum shows that a strong peak for ammonium-nitrate and organic sulfate that is main component in homemade explosives. So the residue of flaky, textural and hygroscopic nature suggests prolonged exposure to the volatile chemicals. You know what's the fun fact? The residue will mix with drywall dust, masking a secondary explosive like TNTP. The hygroscopic samples will absorb moisture, requiring a rapid analysis to avoid the false negatives.
We recommend using supplementary Raman spectroscopy for crystalline ID in future cases.
This aligns with clandestine lab activity. The ammonium nitrate could indicate explosive production or drug synthesis byproducts. Any safety risk during analysis?
So we use a fume hood and explosive PPE.
So, the SAM revealed the fibers were indeed synthetic polyester and not natural cotton. Their surface had embedded crystalline particles consistent with cocaine or methamphetamine residue. Their irregular weave suggests low quality fabric, possibly from protective gear or makeshift lab curtains.
This supports the theory that the site was used for drug processing. The fibers could lead suspects to the scene if matched to clothing.
So the limitations include no dye analysis. We will need microspectrophotometry to trace fabric origin, static interference, distorted sub-images, and carbon coating improved quality but delayed processing. XRF and SEM EDX analysis showed the tools were stainless steel, which is iron chromium alloy, with severe brittle corrosion. Chloride and sulfur deposits could indicate the exposure to hydrochloric acid or sulfur-containing solvents, which is common in methamphetamine production.
This branch wasn't fixing pipes. The corrosion pattern indicates acid spills, and the copper traces suggest pseudo-fredolin reductions. The challenges were pretty obscure tools marking. There are no serious numbers recoverable. The soil collection missed with subsurface residues, and the acid addition might be helpful, but it destroyed evidence.
We also couldn't differentiate household bleach from lab-grade HCl without pH testing, which wasn't performed initially.
Could the tools be traced to a specific purchase? We'll cross-reference tool markings with hardware store records, but the corrosion is likely erased identifiable features. In conclusion, all evidence points to illegal drug manufacturing, cocaine in the powder, explosive residue on the walls, drug-laced fibers, and acid-damaged tools. We recommend further investigation into chemical procurement records and suspect clothing fibers.